Hey guys, welcome back to the channel. Hope you're all having a nice day. I just want to say thank you all for 40,000 subscribers. Not only does it mean a lot to me, but I really don't care too much about the subscriber number, the view number, the ad revenue number, or anything like that. Really what matters to me the most is just seeing how these videos impact you guys. Pretty much my metric of success or anything like that is just how many people reach out to me, letting me know that they got their dream offer in part due to this channel. And that's really what does it for me at the end of the day. So thank you a lot for all the support. I'm probably not going to go and make a slideshow of all those offers just yet. I'll do it in a little bit, batch them up. But yeah, I really appreciate it. Have a great day. Let's go ahead and do some systems design. Okay, so today should hopefully be a fairly fun video in which we'll be talking about a distributed priority queue. Now this one is absolutely killing me because I heavily based it off some Facebook paper that they released a couple of years ago called FOQS, or Fox, I don't know how they want to pronounce it. But the gist is, I was racking my brain for like many hours, even days, on how to build this thing. Came up with what I thought was a pretty good solution, probably overcomplicated it, read their paper, and then I was just like, oh, I could have just been doing this the whole time. That was so much easier. And then I still tried to improve upon it, couldn't do it, realized that the improvement that I thought I made on their design was actually in their paper, and then I felt like an idiot. So I've been humbled by about 10 separate engineers at Facebook, but maybe I'll get them another day. So let's go and talk about what they more or less did. So a company like Facebook or Google or any massive one like that does need something like a distributed priority queue. The reason being that they have tons of jobs that they want to run in an automated fashion, they want to run them asynchronously, and ideally certain jobs are more important to run than others, so they want to be assigning them with some sort of arbitrary priority. So let's say, for example, as you can see I have in the drawing, something like a video encoder. Right? Maybe we've got one video over here with priority 1, we've got the presidential debate over here with priority 2, and we've got a last video over here with priority 3. Basically, our distributed priority queue is going to allow us to build out a scalable and fault-tolerant system with fairly good read and write throughput that's going to allow all of these separate video encoders to basically pick off all of these items and make sure that they all get processed at least once. Cool, so I guess the gist is, the second that you go ahead and hear from a node saying that your video that you want to process is in the system, it should eventually get processed. Cool. Let's go ahead and talk about some problem requirements. So basically, to formalize this out, we want to build an ordered list of items. But of course, it's not enough to build an ordered list of items, right? We've done that with Kafka. We've done that with JMS brokers like ActiveMQ or RabbitMQ. We want to be able to assign them each a priority. Cool, so we have this concept of priority on our ordered list, and we want to be able to support some operations. In queuing, modifying an existing item, we want to be able to dequeue, and probably we want to be sure that if an item is actually in one of these lists, that it is going to be delivered and processed at least once. Typically, the way that you would make sure that results only happen exactly once is you probably have some sort of idempotency key or some sort of idempotent function that's going to be run as a result of handling your message. But I'm not really going to talk about this too much here, as we've talked about it plenty in the past. So the last aspect of this is that we want our system to be both scalable and fault tolerant. So I guess that's not really a functional requirement, but it is something that is going to be required, even if we have billions of messages. Cool, so the first thing I want to do is quickly give a moment to ordered consumption, because you may be thinking, oh, like we want to build this massive queue out, right? And so when we're talking about just like a normal queue or like a FIFO queue, you have ActiveMQ or JMS brokers where I guess the consumption of the messages is unordered, and then you also have Kafka where basically as long as you have one consumer per partition, all of the messages in that partition are going to be consumed in an ordered fashion. So the gist is, I guess the same thing really applies here, right? Can we guarantee that all of our messages are going to be processed in order? Yes, but only if our queue has one consumer at a time. If you have multiple consumers, inherently, in order to take advantage of the fact that you have multiple consumers, you want multiple messages to be delivered to those consumers at once. And of course, if that happens just due to some sort of race condition, one of the later messages can be fully processed before an earlier one. So if this is the earlier message and this is the later message, you can see that the earlier one's delivered first, the later one is delivered second. But ultimately, maybe the later one gets processed first and gets put in some database sync over here, while the early one gets processed second. Now this is going to be a challenge that we inherently have to deal with, but my point is here, we're not going for perfect ordering within our priority queue, because at the end of the day, we probably want to have more than one consumer. If we only wanted one consumer, this would be a very different problem, and we could just go ahead and build like a heap or something in memory. But yeah, okay, so keep in mind that we're not going for ordered consumption, we're going for pretty much like an approximate priority queue. And here's the best way that we can try and do that. So there are a few different ways that we can implement a priority queue. If I went to you after you took your data structures and algorithms class, you would probably say, okay, well, let's do it with a heap, right? And a heap is pretty simple because it allows you constant time accesses of the top element of the heap. So if you're looking for the number with the lowest priority, for example, and it's a min heap, you can easily find that. And then of course, when you pop it, you have to do some logarithmic actions in order to rebalance the heap. So we would implement that as an array, and the question is that something that is easy to implement on disk? Well, probably not, because there are a ton of random shuffles that you have to do of the array element, right? Like a heap would basically be like, this is the first level right here, these two guys are the second level, you know, this over here is going to be the third level, and so on. And so if you're switching elements between this spot or this spot all the time, now all of a sudden you're jumping around that list. It's probably not going to be too great for a hard drive. So how could we do this on disk only? Well, actually we do have a fairly good way of doing it, which is using just like a normal B tree or an LSM tree based index. The reason being that we can actually maintain a sorted list, and because it's a sorted list, we can really easily access the first element. That being said, something like an LSM tree or a B tree based index is still going to be fairly slow, because at the end of the day it is based on disk. And in addition to that, it's basically just going to be the fact that, you know, we'll need an index eventually for some ID of every single node, meaning that we can't perfectly denormalize the data. We're going to have to normalize the data, and so we're going to probably be jumping around the disk a lot as a result of that. And so we're not going to, you know, we're going to have a lot more expensive writes as a result. We have all of these log n insertions into our index. And also if we delete an element from the top of our sorted list, we may potentially have to rebalance our index if it's something like a B tree. So we can have a lot of expensive operations going on in the background there, but also just in general, memory is a lot faster than disk. So what could we perhaps do instead? Well, we may be able to implement some sort of hybrid approach. So in this case, we could actually do the heap itself in memory, or rather the sorted list itself, but some sort of data structure where we basically have a sorted list of all the primary keys of the nodes ordered by their priority. And in turn, what we can do is have pointers to the data on disk. What this allows us to do basically is just insert a bunch of data on disk. When we insert it, which is going to be an O of 1 write to the end of some sort of log, almost like Kafka, then we can basically, you know, simultaneously have derived data in memory, which is basically going to be that sorted index of all of those node IDs. But I'll explain that in a little bit. So to just make sure that this is feasible for the type of scale that we're looking for, well, if every single node needs some sort of priority, and it also needs a pointer to the actual data location on disk, imagine that's 8 bits for the priority, 8 bits for the pointer, that's 16 bits overall. And so as a result of that, if we have a billion nodes, that's 16 gigabytes on disk. So not too bad, actually. We can totally store that, 16 gigabytes in memory, and again, that is fairly reasonable for a modern day server, especially if we start to partition this thing out. Cool, and again, we can do this regardless of how big the nodes are, because our limiting factor is probably going to be memory, and all we really need to store in memory is just this one thing right here. So what does this actually look like to really try and solidify that in everyone's understanding? Well, it would be some sort of hybrid priority queue, right? Where in memory over here, we have a heap or a sorted list, whatever you prefer to do. And then over here on the right, on disk, we basically have something that almost resembles just like a write-ahead log, where as nodes come in, they get assigned some sort of ID based on their location. So that should be super easy to do. We just order everything, pop it into the disk. Then in addition to the ID, we have the actual data. In reality, this is probably going to be pretty big because it could be something like a video frame or a small video chunk or something like that, or anything else that we might want to process asynchronously in the background. And then finally, of course, we have our priority. So regardless of how these things are ordered on disk, when we actually go to memory, we order them properly. And so again, the disk writes are going to be O of 1. Of course, in memory, it's probably going to be O of log n, where there are n things in the heap, because we have to insert it in the proper place of the heap. Cool. Now let's go ahead and talk about modifying some enqueued elements. So keep in mind that one of the things that we wanted to be able to do was basically take an existing element that's on disk somewhere, like down here, and be able to actually change the data, or perhaps even change the priority. Well, if we do that, fortunately, like I mentioned, we're assigning an ID to every single element of our heap as it's going in. And so we can actually use that ID and the fact that this is already going to be sorted by ID, just like an index, and then really quickly figure out where that lives on disk. So that is going to make life easier for us. The one expensive thing to do would be if we actually changed the priority of the node itself, because then we would have to go over here, do some sort of in-memory update, and that's not exactly the easiest thing to do. Perhaps then, instead of doing a heap, we might want to do some sort of sorted linked list with a hash map, where the hash map is basically going from node ID to a particular element of the list or something like that, so that we could access it in constant time. Cool. Hopefully that's starting to make sense. But the gist is, we want all these operations to be atomic. I think it would be really nice if we could just keep everything simple, use something like a standard SQL database, and yeah, that should hopefully make our life a little bit easier. Of course, though, if you are aiming for faster reads or writes, then maybe you'll choose a different database. If you're able to fit everything in memory, that could be great. But yeah, I mean, we pretty much have a write-ahead log right here, and then we also have a separate in-memory index. So you're basically looking for a database that implements a sorted in-memory index for you. Otherwise, you would effectively just build something out like this on your own. Cool, let's talk about replication quickly to get a better sense of what's going on here. So we want to be sure that basically all of our messages are going to be delivered. So what options do we have? Well, for starters, we have multi-leader replication, which basically means that if we want to write to the same node ID from multiple different regions, that we could. That being said, I don't really know that this is going to be a huge requirement of our system. The reason being, I can't imagine that people from multiple different regions are going to be modifying the same task to be processed asynchronously. It could happen, but it seems like, at least for this case, it's probably less likely, and so we're not going to get that much benefit there, and it also comes at the cost of potentially having to deal with write conflicts when that does occasionally happen. In theory, we could do leaderless replication if we wanted some sort of strong consistency, right? So we could try and use quorum consistency in order to effectively ensure that, within a partition of our priority queue or something, that we make sure that every single event that goes in there is replicated sufficiently such that it doesn't get lost. So that's actually not a terrible idea and could potentially avoid us having to do something like a two-phase commit to make sure that all events are synchronously replicated somewhere. But at the end of the day, I think that if we just kind of go towards single leader replication, we may end up getting faster read and write response times. So it seems pretty preferred to me. Finally, we could do single leader replication. However, again, single leader replication is not perfect in the sense that if you write to a single leader and then you're doing asynchronous replication and the single leader goes down before that message gets asynchronously replicated, all of a sudden that message is lost. So what we could do is something we've started to talk about a little bit more, which is use a consensus algorithm with some sort of like replication group where, let's say every single leader has 2 followers. That message has to be synchronously replicated to one of the followers before we can proceed, right? Because that's kind of how something like Raft works. You have to get a majority of nodes to agree that the message is real before you can proceed and consider it a successful write. So we can do that, and the nice thing about that is that when we do see that a certain node exists, we can just read it from the leader, and then we only have to read the message from one place, so that actually helps us with our read speeds compared to something like quorum consistency. Cool. Let's go ahead and talk about partitioning. So we want to basically make our read and our write throughput as fast as humanly possible because we want this thing to be a massive system at scale. So what does that really mean? Well, it means we want to decrease our read and write load from a single node in any of our partitions. So another thing to note is we're already handling message events out of order, right? I mentioned that we're likely going to have multiple consumers here as opposed to just one. And because we have multiple consumers anyway, it basically means that we're never going to get perfect ordering. And so actually using something like round robin will probably be the most fair way to distribute events by their priorities. Or rather not by their priorities, but just completely randomly. And that way we can ensure that you have consumers reading from every single node. And as long as they're doing that, even if we're not getting perfect priority ordering across all nodes, we're still doing this pretty well. Another option as opposed to round robin would actually be to partition by priority, or like by the range of priority. But the problem with that is assuming priority is like a continuous value and there's not just like, you can have 1, 2, and 3 priority. Assuming we can literally have any number as our priority, then what that could lead to is a lot of hot reads on the top shard, because at the end of the day, when you're doing a priority queue, all of the reads are going to be coming from one node. So even though the writes may be spread out, first of all, there could be an uneven distribution in the priority ranges provided, but also the reads are going to be completely locked in on that one node. And because we're not getting fairly ordered writes anyway, because we have a bunch of consumers consuming from that one node, it doesn't really benefit us to be only consuming from one place. So I thought a lot about this concept of like trying to partition by priority when I was thinking through this video, but ultimately doing this thing round robin and basically just randomly spreading out events is probably going to be the best way to get this done. Cool. So now we know that we have events going to many partitions, right? So this could be like partition 1, and we've got our little like heap in memory and data on disk. This could be partition 2. This could be partition 3. It is possible that we might have one particular consumer that is actually reading from multiple partitions at once. So if this were to be the case, how would we go ahead and do it? Well, actually, we would probably want to make sure that we're aggregating the data across all 3 of these nodes at once, and then picking the one with the highest priority across all 3 of them. So the way that we could do that is basically by having a consumer over here establishing its own little heap in memory, and basically picking from the top of the heap. So this could be the one from partition 1, and then it'll have to reach out to partition 1 again to basically backfill this heap once this guy is processed. So the way that we can do that, at least in my opinion, is probably going to be best done with something like a long poll. The reason being that using a WebSocket here, a server sent event, especially if our queues are, especially if our priority queue is not especially busy, it basically means that we're going to be maintaining a persistent connection when probably most of the time we don't need to maintain that persistent connection. If these events actually take a fairly long time to process, then this guy's going to have a lot of downtime where it doesn't actually need to ask for another event. And so just fetching one event as opposed to maintaining a persistent connection the whole time seems like a much better solution here. I also wrote downtown instead of downtime because my brain doesn't work. That's a shame. Cool. Finally, let us go ahead and go into our actual design. So again, we've got our client on the left. This guy is someone who is going to be publishing to our priority queue. When we do that, the first thing that we do is hit our load balancer, which is going to use round robin. The reason being is that we can't ensure a perfect ordering of all of our events by their priorities as long as we have multiple consumers anyway, so we may as well approximately spread them out and just have our consumers listen to certain priority nodes. That's going to make our life a lot easier. Then over here, basically the kind of priority queue itself will be held on a MySQL database. So effectively, we're just inserting in primary key order, like right into a log, ideally O of 1 inserts onto disk, and then separately maintaining this derived data structure of a heap over on memory. So in memory, we're basically going to be indexing on the priority score. And then of course, within our partition, like I mentioned, we're going to be doing some replication with Paxos or Raft or any other consensus algorithm. The reason for that being that once we've actually properly done that Paxos or Raft algorithm, we can be sure that the message is going to be fault tolerant and will eventually be read. That is an extremely important part of this. So what does that look like in real life? Well, it basically means you propose to one node, you propose to another node. This is the propose phase. They both come back and say whether or not they'll do it. It almost looks like a two-phase commit, except the difference here is that you only need a majority approval. So if this guy doesn't actually ever respond because he's down, we only are able to send the message to the other node right over here. But since we got a majority approval and that node goes through, we can actually go back to the client and say, hey, you wrote successfully, your thing is in our system, it's going to get processed. Now, of course, from there, we have our consumers. So it's possible that you could say have one consumer sharing a single partition with another consumer, and if that were to happen, you would basically use locking over here to ensure that they're both not receiving the same event. And then of course, once they acknowledge that event, that they've handled it properly, that event is then deleted or marked as deleted from the MySQL table. Cool. Additionally, if you have a consumer over here that is handling multiple partitions, then we have to do what I described before, which is basically do long polls to the nodes that they care about, aggregate some sort of local list where you get the priorities of each node and figure out which one's the next one that you want to handle, and then handle them accordingly, writing back to the database and saying, hey, I just handled your last event, please give me your next one of highest priority so I can consider that. Well guys, hopefully you found this fairly useful. Again, this is not really my design. I kind of just stole it from Facebook, which is a nice feeling. But it is a fairly good design, and I see why they use it, and I see how it does scale. So props to them for that one. Anyways, hope all of you have a great day. Thanks again for the channel Landmark, and enjoy your weekend.